Okay, so no video of me if you're listening at home. So just follow along. You'll be all right. So day 2, day 1 was the long way, the definition way. Day 2 is a power rule. This is a shortcut way. So the shortcut is awesome. It is a great shortcut. But we're going to kind of walk our way until we get there. Friday's lesson was, here's the formula for getting the formal definition of a derivative. And remember that part of it was just good old Algebra 1 slope. That was what that was. But then we throw this limit on there, and that turns it into a calculus slope, turns it into a instantaneous rate of change rather than just average rate of change. So very much related to each other. But you might remember as we shrunk that delta x down to 0, we went from 2 points to 1 point, and that limit process is calculus, and that's how you get derivative at a point rather than slope across 2 points. Okay, so pretty cool when they figured that out. Like, that's pretty neat. But like, this can get kind of rough, kind of ugly. We're not going to walk through all of these steps. This is just showing the steps for if you wanted to do the formal definition of an x cubed polynomial. Like, here's what the steps would look like. And there's nothing that's beyond you in that. It's just that's a lot of things to keep up with. Look for things to cancel, reduce, plug in. Like, eventually you get there. But what I want you to try to find, and I'm going to rewrite this right above it because it might help. See if you can figure out the shortcut. And it goes term by term, so look at one term at a time. See if you can figure out the shortcut rule to get from the function to the derivative. Can you see what the shortcut is? Anyone want to try to verbalize what the shortcut is? Okay, multiply by the exponent, and one more thing, that's step 1.
Drop the exponent by 1.
And decrease the exponent by 1. That's it, that's the shortcut. Yeah, we'll phrase it the way you guys phrased it. Multiply by the exponent. I've been saying, like, make it the coefficient or take it down as a coefficient, but multiply is the same thing. And then reduce exponent by 1. So exponent comes down front, multiply by the exponent, and then decrease the power by 1. Now, a couple of things toward the end here. From 3x to 3, remember that the derivative tells us the slope. So if we zoom in on 3x there, the slope of 3x, that would just be a line with the slope of 3. Now, it still fits the shortcut rule, but it's also just knowing the slope. 12 is maybe a little harder with the shortcut, because it's like, well, what exponent? I don't see an exponent. But you could make that x to the 0, and then when you multiply by the exponent, it zeroes it out, and it doesn't matter what you do after that. So that's one way to think of it. The other way to think is the line y equals negative 12. What's the slope of that line? 0. So that's why the derivative of negative 12 is 0. So derivative of a constant is 0. Derivative of a line is whatever the slope is. But they all follow that shortcut rule. So go ahead and answer that bottom question down there. We'll definitely call on people today, because even though it's our very first one, pick on 2 people. So, Nathaniel, what is the derivative of 7x to the 9th?
63x to the 8.
63x to the 8. Multiply by the power, decrease the power by 1. 63x to the 8. Grayson, how about the derivative of the second piece there?
48x to the fifth.
48x to the fifth. Yep. Pretty easy when the process is easy. We're going to make it harder in a minute, but how hard can you make it if all you're doing is multiplying and subtracting 1? 1, 2, and 3. Oh, hold on a second. The box up here, this tries to make official what we already said. Like you multiply by the exponent. Multiply by the exponent. And then decrease the exponent by 1. So it's exactly what you guys already said. It just looks a little fancier with n's and x's and stuff in there. Okay, 1, 2, and 3, I'm going to let you try, and then we'll check them. The main thing about 1, 2, and 3, or at least part of it, is we're using different terminology. So number 1 says find f prime. Number 2 says slope of the line tangent to the graph. Number 3 says instantaneous rate of change. But all of those mean derivative. So it's just making sure you understand we can call for a derivative a bunch of different ways. So try 1, 2, and 3. Power rule is easy. How we can try to make it difficult is a couple things. One is use different names for it, but that's really not that big a deal. It's kind of the only thing we're doing right now is taking a derivative. So I could put gobbledygook under there, and you'd probably just think, well, I guess I'll take a derivative. So make sure you know what those names are. The other way to make it tricky is when we get to 4, 5, and 6. Because it's called the power rule, it's not called the root rule or the denominator rule. So I need to change this into powers. So I need to do some algebra before I take a derivative. So I'm not taking a derivative, I'm just algebra-ing my way through this. Meaning I would like to write the cube root of x as x to a power. So then I could use the power rule. So what power is the same thing as a cube root?
1/3.
1/3. This was very much related to the bonus on the test, which are not graded, by the way. So sorry about that. How about 5 over x cubed? How could I rewrite that? How else could I write an x to the negative 3? And then the last one has like some of everything wrong with it because we got roots, powers, and denominators.
7 x to the negative 2/5.
Right, x to the negative 2/5. Remember the flower power grows on top and the root grows underneath. That's the silly way to remember it, but if it helps. So the power is 2, the root grows underground, so that's 5. And yeah, the whole thing is underneath, so negative. Okay. Now we're ready to use the power rule. Be careful. It's the same rule. It's just now that fractions and negatives, people will start panicking and doing weird things. So 1/3 down front. And yeah, you can do derivatives, but can you do fractions? Guess we'll find out. Cole, what's 1/3 minus 1? If I decrease 1/3 by 1, what do I get?
That's negative 2/3.
Yes, it is. Negative 2/3. All right, the second term, I bring the negative 3 down, so that would make positive 15. And Ty, if I start at negative 3 and I decrease that by 1, what does that get me?
Negative 4.
Yes. I would say that is, Ty got it right. Somebody earlier today got it wrong. That is a frequent mistake spot right there. Do you want to guess what people put right there?
2.
2, or negative 2. Because they're thinking decrease, so that goes from 3 to 2. Like, well, yes, but if you're in the negative, decreasing means getting more negative. Last term, negative times negative is positive, so positive 14/5. Oh, we're really going to press somebody's fraction abilities here. Will, what's negative 2/5 decreased by 1?
Negative 3/5.
Negative 2/5 minus 1.
Oh, -7/5.
There you go, -7/5. And again, like most people are fine on the calculus part, it's just the fractions and negatives and negative fractions that start messing people up. That's a perfectly okay answer. I would be careful. Multiple choice, like we could get sort of creative and fix the negatives and put things sort of back where they go if they're negative. I don't know that I would do this, but some people might think that's cleaning it up better if you did that. But if it's a free response question, I would not do that for sure. I would leave it. Number 5, find the derivative of this thing. Number 5 is trying to like bait you into taking a derivative of the top and then taking a derivative of the bottom and then dividing. But it doesn't work that way. You're not allowed to do that. There is a quotient rule, and it's kind of complicated, and we'll worry about it later. But for now, let's do algebra first, kind of like we did on the last one. So let's just divide all the terms by x squared. So 2x squared minus 3x plus 9 minus 7/x, but I know I don't want over x. I want it as an exponent. So that would be x to the -1 plus x to the -2. So 5 people get to help us on this one. We'll just go in order here. Let's see. So in order, Alyssa, what's the... Ooh, I almost made a terrible mistake. Students do this all the time. Shame on me. If I'm about to write the derivative, it definitely does not equal y. So I need to say dy dx equals. It's not multiplying either. That's just like a break. Okay, Alyssa, what's the derivative of 2x squared? 4x. Kenneth, how about the derivative of -3x? Minus 3. Ethan, the derivative of 9? Nothing, 0. Just to kind of hold the spot, I'm going to put plus 0. Obviously, you don't even need to include that. Abby, how about the derivative of -7x to the -1? Good. 7x to the -2. And then Kinley, the derivative of x to the -2?
-2x to the -3.
Very nice. So again, the problem with that one wasn't really the power rule. The problem was the algebra that we started with. And again, you could clean that up a little bit if you wanted to by putting x squared in the bottom and x cubed in the bottom. Kind of depends on the problem, the teacher, the test, what you would do from there. Try number 6. Try number 6. So, a little bit more because we can. Like that's pretty straightforward stuff. Let's talk about differentiability. Sounds fancy, but differentiability just means has a derivative. And that's what the paragraph says. A function is differentiable at a point if the derivative of the function exists. So it's just a fancy word for it has a derivative there. This is big because this will help. Remember that the derivative of the function is the slope of the tangent line to the graph of that function. So the derivative tells us the slope of the tangent line. Okay, so what do you think could be happening? And these 3 exceptions, you've seen them all before. You just haven't had to think of these exceptions in terms of derivatives. So yes, this is different and new, but you're going to be familiar with all of these examples. So it's not differentiable if. So can you think of graphs that you've seen where it would be impossible to know the slope of a tangent line at a particular point? Sorry, there's 3 guesses here, and I think first period got one of them, and second period didn't get any of them. So
It doesn't exist.
okay, so if the function doesn't exist, I'm not going to put that here because we're assuming that the function exists at x equals a.
Sure.
But you're right, if the function doesn't exist there, then there's definitely not a derivative there. So I mean, that's a good point, and we do ask that kind of question. And students are like, wait, what is the derivative? There's not a function there. I'm like, yeah, if there's not a function there sure can't be a derivative there. So you're not wrong, but this is not what we're talking about right there. What's that? But a straight line has a slope. It's like a constant slope. A horizontal. Okay, now we're getting somewhere. A horizontal line. What's the slope of a horizontal line? 0. Okay, so that's fine. But what's the slope of a vertical line? Undefined. So it could have a tangent line, but if that tangent line is vertical, its slope is undefined, which means its derivative is undefined. We're going to put that as number 2 just so it'll match all the other notes we have, or I have. I guess it doesn't matter to you. If f has a vertical tangent line, so what that would look like is if there's some point where the graph turns straight up, even if it's just for a quick second, and there's a vertical tangent line there. So the graph exists, there is a tangent line, but it's vertical, meaning the slope is undefined, like you guys said. And if the slope is undefined, I don't know that equals is even the right word there. If the slope is undefined, then dy dx is undefined. No y prime. So that one's kind of tricky because there is a tangent line, but if it's vertical, there is no slope, which means there is no derivative because slope and derivative mean basically the same thing. Okay, so you guys got one of them. Okay, asymptotes is a good guess and it kind of fits this, but asymptotes, there's no function there. So that fits with what you said earlier. You're right, there's no derivatives at the asymptote, but that's because there's no function at the asymptote.
So would be whole either.
Wait, say that again then? A hole. If there's a hole there, you can't have a point
They're all
there.
the same.
But if there's a hole there, then it looks like, let's roll with that one. If it looks like this, so the function exists up there, but how are you supposed to draw a tangent line to a point that's just like floating out in space? Like, how do you know where the tangent line should be? So I'm not going to say hole, I'm going to be a little more generic and say f has a discontinuity. Which should be a hole, or a jump, or an asymptote. And again, asymptote's weird because it kind of fails because there's not even a function there. But there's your 3 discontinuities: holes, jumps, and asymptotes. 3 not differentiabilities are if it's discontinuous, even though the function exists, like you can't draw a tangent line at a jump or on a point by itself or at an asymptote. Okay, there's one more example, and you're probably only familiar with one function where this thing happens. You're all familiar with it, but a spot where you can't draw a tangent line. It is absolute value. Because how are you supposed to know what the tangent line is at the point? It's like if we drew it the other way, it'd be like a seesaw. Like, how do I know where the tangent line is? And so if f has we use different words for that, a corner, a sharp turn, textbooks call it a cusp. Those all mean the same thing. If there's a sharp turn, then there's no way to get a tangent line there. So it does not have a derivative there. Okay, corner, cusp, sharp turn. I guess there's other things. There'd be no way to draw a derivative there, to draw a tangent line there. Okay, so the three not differentiability spots are discontinuity, vertical tangent line, and corners or cusp or sharp turns, whatever you want to call them. And again, this is a little bit weird maybe because within the discontinuities are holes, jumps, and asymptotes. So kind of like Venn diagram kind of situation here. Okay, some examples. State the values of x at which f is not differentiable. Well, anything that makes the bottom 0 means it's not continuous. So it's not differentiable at x equals 3. Now, if there's more going on at x equals -3, and we could do some more work to figure out what's going on there. But before I do that, I don't have to go any further. This thing is not continuous at -3 because it doesn't exist at -3, so there can't be a derivative at -3. Now, again, if we do a little more work, the x plus 3's will cancel, so we know there's a hole there. But I really didn't need to know that to know that there wasn't a derivative there. That's a -3, and that's a -3. All right, number 2. I don't immediately know what that graph is. I mean, it's sort of a parabola, but the absolute value thing means if it's ever negative, make it positive. So, like generically what would be happening is, there's our parabola. But anytime it drops below the x-axis, the absolute value would flip it to the other side, and then we would have some points, some cusp or sharp turns there. So how do I know where those turns are? Yeah, where the inside stuff equals 0, because that'll be where it bounces off of 0. X squared minus 5x plus 6 equals 0. So at 3 and at 2, it is not differentiable. Make sure we answer the right question here. Not differentiable at x equals 3 and 2. Number 3, find the value of x at which the cube root is not differentiable. There's maybe 2 ways to do this. Do you know what the graph of the cube root looks like? If we knew that, maybe we could get it from the graph.
Oh, yeah, it has a straight.
Some of you are sketching out things in your hands. Yes, it looks like that. And I'm not sure that even does it justice, because that doesn't look like there's a spot with the vertical tangent line. So maybe we should sort of prove this to ourselves rather than just guessing that at 0 there's a problem, because I don't know if there is or not right now. So if we take a derivative, 1/3 x to the -2/3, which means I could bump the negative thing into the bottom, so x to the 2/3. And so yeah, x can't be 0, because dividing by 0 would make infinity, and so that does mean that there is a vertical tangent line at x equals 0. So it's not differentiable at x equals 0. Everywhere else is fine, but x equals 0 is a problem. Number 4. Tricky in an easy way is number 4. State the values of x at which that thing is not differentiable. Again, not differentiable means we're looking for where it's discontinuous, where there's a vertical tangent line. I'm just repeating these from earlier so I know what I'm looking for. And corners. So I don't know what negative 3x to the fifth plus 3x squared minus 9x plus 11 looks like. But I can say something about its differentiability. Any guesses or thoughts? Let's see, negative x to the fifth would mean it's going down on the right end, up on the left end. Might be 4 turns, so something like that. But it's always continuous, so it's not discontinuous. There's no vertical tangent lines. There's no corners. And so polynomials are everywhere continuous. Or, excuse me, I'll go one further. Everywhere differentiable. They're also everywhere continuous, but differentiable is a little more stricter criteria. They're smooth and they're continuous with no vertical tangent lines. So we use a lot of polynomials in calculus because they're differentiable and we can do all the derivative things with them. Number 5. Which of the following statements is true? Limit as x approaches 3 exists. So what do I have to do to check to see if the limit as x approaches 3 exists? This is similar to, I think it was the last one on the test. What do I need to do to check to see if the limit exists? Do you remember? I haven't graded your test, so I hope you're just being quiet. I need to check the limit from the left. So that would be the left limit. And the limit from the right, and see if those are the same. So left limit equals right limit, that would mean the limit exists. So the left limit would be when x is less than 3. So 3 plus 2 is 5. The right limit would be when x is greater than 3. 4 times 3 minus 7, that's also 5. So those are equal to each other, so yes, they're both headed toward 5. Okay, for continuity, that would mean, and I needed to see this on the test, the left limit equals the right limit equals the function value. F of 3 would be in that top one. 3 plus 2 is 5. So I've got all 3 of them now, so now I've proved they're continuous. And again, I needed to see limit statements on the test. A few of you wrote things like 1 equals 1 equals 1. I'm like, well, yes, that is true, but I don't know what you're talking about, so I need more than that. Right? Like, I know what you did, but you need to tell me what you did before you just write that. Okay, differentiable at x equals 3. Okay, so that means the derivative at 3. And I kind of need to check the derivative from both sides. So it's a similar process, but instead of checking the function, I'm going to check the derivative. So I know they meet at 5, but I need to know if they meet at a corner or if they meet smoothly. So the derivative of x plus 2 would be 1, and the derivative of 4x minus 7 would be 4. So no, the left y prime would be 1, and the right y prime would be 4. So no, it is not differentiable. There is a cusp there. So that's enough. I'm going to sketch out what this would look like. So we know when x is 3, y is 5. Now to the left of that, we have a slope of 1. To the right of that, we have a slope of 4. So there's our cusp, not differentiable. But we had to check both. You had to check that the function was the same, and that you had to check that these slopes were the same, so that it makes a smooth transition from one to the other. All right, why don't you try 6 and 7? And I guess I would just say, when you read 7, read the question. Don't just skip to the answers. Those are not points. Those are intervals. So 6 is talking points, 7 is talking intervals, but it's kind of the same question. Where is f continuous but not differentiable? Number 8. Second. So number 8 is E. Number 9, absolute value. I think I can get to everybody today. Get 3 more questions in. Annie, is f continuous at 0? Yes. Simon, is f differentiable at 0? Why not? It's a cusp. And Phoenix, is f defined at 0? Yeah, there's a point there. So 1 and 3 only. Nicely done. Got to everybody. All right, assignments worksheet 2. Tomorrow notes are a little shorter, and we'll have time to answer questions from both worksheets.